This is problem 34. It's all about magnetic fields and the force they apply, and as a result, the torque in this problem, and the torque created by weight. So this is a great video to review not only some stuff about magnetic fields, but also torque. So here's the setup. We've got current going up and to the right through this thin uniform rod, and that's a key word here, that it is a uniform rod, and it's in a magnetic field. Since it's a uniform rod, let's address first the fact that it does have a weight, but just like uniform planks, we can pretend the weight's all in the center. So I'm going to have a torque, and I'm going to draw a couple of pictures here to help us with this. I'm going to have a torque due to the force of the weight like that. Okay, so I extend a line through the force, drop my lever arm, and there's a torque due to that. To get the weight, it's 0.094 kilograms, so our weight will just be 0.094 kilograms times 9.8. And I'm not going to worry too much here about the signs, because in this problem, this rod is not supposed to rotate. So I'm going to do like absolute value of one torque equals the other. So I'm not going to sweat the signs too much. And we can get a number there for the weight. Let's go ahead and get that since I have it up already. So 0.094 times 9.8, 0.9, let's call it 92 newtons. And I can get my lever arm in terms of theta, which, let's see, did they give us theta? Oh, we're trying to find theta, but the thing doesn't rotate. So it's good that I'm getting theta into an equation already. That little circle that just got filled in there is theta. All right, so this torque will be, or the absolute value of this torque will be 0.92 newtons times, here's our theta, and we want L. And they gave us 0.45 meters. So we're looking for this L. Here's our right triangle. This will be 0.545 meters cut in half. So 0.45 meters, cut that in half, times, let's see here, adjacent and hypotenuse. So that'll be the cosine of theta. So this right here is our lever arm. Okay. If you can't see what I'm doing there, I'm going to rewrite this out just to make it clear. Cosine of theta equals the adjacent, which is L. That's my lever arm, this distance right here, over the hypotenuse, which is my 0.45 meters cut in half. It's half the rod. So L will be this times cosine theta. So that's where that came from if you were not seeing the trig. So I've got one of the torques. Let's call that torque due to the weight. Now I need to get the other torque and then set them equal to each other. So the other torque, the torque due to the B field, the absolute value, because again, I'm playing fast and loose with the signs here because I'm using absolute value. Because I know there's only two and it's not going anywhere, so they have to add up to 0, that kind of thing. If you wanted to use signs, counterclockwise is positive and clockwise is negative. The other torque due to the B field will be the force of the B field. And I'm going to draw another picture here for this one. Here's my pivot point. And here's the direction. Oh, better do this. So current's going up and to the right, magnetic field in. So my force is up and to the left. Up and to the left, or my picture here. Magnetic field, get closer for you guys. Magnetic field in. My thumb is pointed that way. So my force is up and to the left. And it is perpendicular. There's the force of the B field. Force of the B field. It is perpendicular to this distance, which makes it really easy. If I extend a line through the force, dot, 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 and drop a perpendicular from the pivot point, I'll just get this right here, which is that whole 0.45 cut in half, just like we had before. Again, this is true for a uniform thin rod like this, for both of these forces to be smack dab in the middle. So to get our torque, it'll be FB times our 0.45 cut in half. And what is our force over a magnetic field? Well, since it's a current carrying wire here, we can use Philb, or F equals ILB, and we're already at a 90-degree angle, so cosine of 90 is 1. So let's substitute that in. So they give us the current, I'll write it out here, ILB times my lever arm, and my current is given as 4.1 amps. The length of the rod, the entire length of the rod is 0.45 meters times the B field, which is 0.36 and then times my lever arm. So this 0.45 is here, not cut in half, because that's the force through the B field on the entire wire. We're pretending it's all in the center because it's uniform. And then the lever arm part is the 0.45 cut in half. So this is some number. In fact, let's get both of these torques as a number. And then with one variable up here, I'm going to section off my work just a little bit. So I'm going to get this with the theta in it and this number. Just going to plug and chug some numbers into the calculator here. I guess keep my password off the screen, maybe. Attempt to. Not a big deal, even if it's on here. All right, so we got 0.92 times 0.45. Cut that in half. Oh. How about divide by 2, not 0.2, or not point. So this is 0.207 newtons times a meter is the units, and then I got a cosine theta on here. I'm going to rewrite that. So cosine theta times 0.2, 0.207 Newton meters. Okay. Cosine theta, 0.207. There's the two numbers. Okay, and then down here, 4.1 times 0.45 times another 0.45 times 0.36. Yep. And then divided by 2, I'm getting 0.1. Go ahead and just round that off to 0.15 newtons times a meter. I'm not going to show how the units work out on that. If you really want to, you can. Now I'm going to set these two torques equal to each other. So this is my torque through the weight, torque through the B field. Here's the big idea. If we're not going to have any rotation, these two torques have to have the same magnitude, opposite directions, but same magnitude. And torque B, 0.15 Newton meters, equals torque due to the weight, which is cosine theta times 0.207 Newton meters. The Newton meters cancel, and I can solve for theta. So I'm going to take 0.15, divide by the 0.207, and take the inverse cosine of that. So inverse cosine of, we'll go ahead and get 4 digits here, 0.7, or 3 digits, 0.725. That should get us close enough. Hopefully I'm in degree mode. I am not in degree mode. I'm in radians because that answer did not make any sense. All right, let's check, make sure I'm in degree mode now. Yep. All right, so let's try that again. So the inverse cosine of 0.725, and I'm getting a theta of about 43.5 degrees for this thing not to go anywhere. Let's see what the book got for 34. Uh-oh. Book got, oh, no, we're okay. The book got 44 degrees. I did some rounding in here, probably a couple places. Definitely not following sig fig, so I did some rounding in here. So that's close enough. We're fine. The book, if you have looked at the key, they're deriving an expression for theta. You could do that. Since all the numbers were given, I went ahead and plugged in. Same exact process, just leave the variables in until the last step. The other way you could have done this that would have looked a little bit different, I'm just doing a little side here, although if you understood this, you're good to go. You could have done summation of torques equals 0, and then I would have had torque. Let's see, which one did which? The weight was clockwise, so it'd be negative torque of the weight plus torque B equals 0. That would be another way to do this. And if you don't like the absolute value stuff that I'm doing here, you could do this, and you'll get the exact same result, because obviously now torque weight equals torque of the magnetic field. And there you've accounted for the sign, so you don't need the absolute value. If the calculating the lever arm stuff back here wasn't clear, there is a separate video just reviewing how to calculate torque. Take a look for that. That's it.